Alright, we're going to finish up kinetics and talk about a model for chemical kinetics, as well as what we're going to refer to as catalysis or catalysis, where we're going to talk about how a catalyst actually speeds up a reaction. Okay, so we got to talk about what's called the collision model, and I've touched on this before, but it's a model to explain current node characteristics of reaction rates. And what we talk about is it's based on the idea that molecules must collide in a certain way. And I always like to think of it like puzzle pieces, that if you have two puzzle pieces that you try to stick together and they're not connecting the right way, it's not going to matter. But if you find the right way, you're going to make something new, and that's kind of how I think of the collision model. Now, typically, if we increase the temperature, we can speed up the rate with which it happens. Okay, that's sometimes why in lab, why we heat a reaction, or we do a hot water bath and then we put the reaction in the hot water bath, is to speed it up, to make it go faster so that we can actually observe it in the time we have allotted. And we can do the opposite as well. We also can slow down the temperature so that we slow down the chemical reaction. And that was why refrigeration was such a major thing with food spoilage, is that you all of a sudden could turn the temperature way down on these substances, slow down the bacterial growth, which is, a chemical reaction in essence at its basic level, and was a big deal. So now most K values increase exponentially with an increase in Kelvin temperature. So it's not just doubling. You're talking about exponential values. So you're talking about 10 times faster, 1,000 times faster, 10,000 times faster, etc., etc. Why? Well, if you increase the temperature, it all comes back to this, we increase the kinetic energy of those particles. And if they're moving faster, then it means that you have an increase in the number of collisions, which means an increase in the number of correct collisions. And the reaction rate is much smaller than the collision rate because most collisions don't result in a reaction. So the collision rate's always going to be higher than what actually connects and causes a chemical reaction, but they still are related, because if you increase the temperature, you're going to increase the kinetic energy, you're going to increase the collisions, but the amount of times those collisions go right, which is the reaction rate, is still smaller than the total of the number of times that things bump into each other. Okay. Now there's a couple of reasons for that. First of all is the energy associated with the reaction. And the activation energy, or the E with a lowercase a, is going to be the threshold energy that must be overcome for a reaction to occur. Now, typically, you may go, okay, where does that energy come from? Well, the energy that they have is going to have the kinetic energy of those molecules before the collision takes place. And then what happens is once the collision takes place, it's converted to potential energy to break the bonds and to change the arrangement of the atoms. Okay, so they're not going to really ask you to describe which is kinetic and which is potential, just understanding that there has to be energy that has to be overcome, and that's what this is right here. Okay, if this is our reactant, and if you look at the axes here, we're doing, I realize, way more graphing than we have in a while. But here's our potential energy. Here's our reaction progress. You could still think of that as time, even though we're not defining it. It's just how the reaction is taking place. Here's your reactant, and here is the activation energy we have to overcome. So in essence, these guys that are going to collide have enough kinetic energy to get them over the hump. And then on the other side, you have your product's energy. And for the most part, what we refer to as typically spontaneous reactions, you're going to get a lower in energy of those products. Okay, so you're going to release energy in the environment. It's going to be exothermic, which, if you remember, makes things happy. The whole goal for atoms is to have the lowest energy possible. And this is just showing you, kind of a ball and stick model of that. Now in exothermic reactions, again, products have lower potential energy than reactants. In endothermic, it's going to be just the opposite. The products are going to have more potential energy than the reactants, and that's why they require energy to be inputted into the system, because you have to make up that difference. And it's not necessarily the delta E that affects the rate. It will affect whether or not something is spontaneous, but the activation energy does, because how much energy is required to get over that hump is going to dictate how fast or how slow that happens. Now this is just showing you graphically, yeah, with a graph, the number of collisions related to energy. So here you have, as temperature is increased, and this is just showing you right here, for temperature 2 is greater than temperature 1, more collisions have enough energy to react. And so what you get is, here's your activation energy. So this is just a linear interpretation of that kind of relationship, where for T2, you're going to be able to lower that energy faster, and it's going to lower the activation energy. So they're going to have more things. Excuse me, the number of successful collisions, and then you have this lovely value over here that we're going to talk about. Remember, E is kind of like our exponent. EA is activation energy, R is our ideal gas constant, T is temperature, and we're going to deal with some equations here that have this in it. Now for orientations, again, this is just, do things collide the correct way? Here you've got the two bromines that need to combine. That you need to combine in order for them to turn into the new product. Over here, again, you have a different way that they collide. Over here, the oxygens aren't the one that are going to react, so when these two collide, nothing happens. So this is just, again, showing you the different options for when things combine. Now, bear with this math. We're going to do some sample problems that hopefully will make this make more sense. I'm just going to throw that out there before I start talking about it. Molecules must collide with certain positions. Here comes the math. Z is what's called this collision frequency. You've got your K, your kinetic constant. And now just let me get to the proof, so to speak, here first. P is what's called the steric factor, which is a fraction of collisions with the right orientation. Don't necessarily worry about those. They're more just the background to get to the proof of what is called the Arrhenius equation, which is this over here. And there's a couple of different forms, and we're going to use this a few different ways. Essentially what we've done is A is equal to ZP, which is what's called a frequency factor, and this is a form that's in linear y equals mx plus b, and we're going to do some graph problems related to this. So again, once we get through the practice problems, hopefully you'll see how, in other words, how we can solve problems using that, which is really why it's going to be the most important. And then over here you have this is used to compare two sets of temperature and K values for the same reaction. So all you're doing on this one is its expanded version, where you have K2 that's going to go with a second temperature, and you have K1 that's going to go with a first temperature. So I'm going to walk you through these problems in class because just because you may want to take a look at it in your book and see some of the problems they have done, but we'll do these in class. Okay, catalysis or catalysis is going to be another way to speed up the reaction. Instead of increasing the kinetic energy, the catalyst is going to actually lower the activation energy. And we've used catalyst a few times. We haven't really studied the mechanism of it, and it's never consumed in the reaction, so it's not considered to be a reactant really, or a product. It's just there, but for whatever reason it helps lower the energy of that reaction, primarily because it creates a new pathway with lower activation energy. And kind of skimming over the specifics, but that's the basic take-home message on that. And so therefore, if you can lower the activation energy, more collisions will have enough of that energy to get over the hump, so therefore you're going to increase the rate and increase the amount of product that's being formed. And this is just showing you right here. Here's an uncatalyzed pathway where the activation energy is going to be higher, and then you have a catalyzed pathway, which again is just going to have a lower activation energy, so you're going to get more things produced. This would be an example of an endothermic reaction, because our delta E would be positive. Okay, like that. Now we do have a little bit of terminology, and this is really just some, throwing some things out there. We talk about a heterogeneous catalyst if it's in different phases as compared to what's reacting. We call it homogeneous if it's in the same phase, which is no different than mixtures. Remember, mixture is heterogeneous. You can see the visible parts and pieces. Homogeneous, you cannot. This again is just showing you the number of collisions with a given amount of energy is going to be a pretty small percentage. So this is uncatalyzed, whereas if you add in that catalyst, you're going to have a larger portion that is going to, remember, you got to look at what the graph's telling you. This is number of collisions versus energy. So in this case, you have more collisions that have enough energy. An enzyme is a very common catalyst found in the body and in biology. Most of the reactions that we run in the body have an enzyme to code them to even happen. So the body is just an extreme case of a lot of enzymes and catalysts. Okay, that does it for kinetics. Hope